What if the internet isn't really in the sky, but deep under the ocean? Welcome to Sleepy Systems. Tonight, we're exploring the hidden cables carrying almost the entire world's internet beneath the sea. Before we begin, leave a comment telling me where you're watching from. And do you think satellites could ever fully replace these cables? Don't forget to subscribe for more relaxing documentaries. Most people imagine the internet as something almost weightless. Invisible signals floating through the air. Satellites quietly blinking above the clouds. Wi-Fi drifting through bedrooms at midnight while entire cities sleep beneath it. The language itself encourages that illusion. We talk about the cloud, as if the modern world somehow escaped the physical limits that defined every civilization before it. But somewhere far below the Atlantic Ocean, in total darkness, under miles of freezing pressure, pulses of light are racing through glass at nearly the speed of physics itself. And every second, those tiny flashes carry stock trades, military communications, YouTube videos, FaceTime calls, search results, banking records, arguments, confessions, breakups, and billions of private thoughts between continents. The strange part is not that this system exists. The strange part is how rarely anyone thinks about it. Because the modern internet is not floating in the sky, it is lying on the bottom of the ocean. Nearly 95% of international internet traffic moves through submarine cables stretching across the seafloor, quietly connecting continents through one of the largest engineering systems humanity has ever built. Satellites do play a role in global communication, especially for remote regions, navigation, and military systems. But for ordinary internet traffic, they are often slower, more expensive, and limited by physics in ways fiber optic cables are not. A signal sent into orbit must travel thousands of miles into space and back again. Light moving through a cable under the ocean usually reaches its destination faster, which means that every time someone in New York opens a video hosted on servers in Europe, or a trader in London reacts to market data from Chicago, there is a good chance their information is crossing the ocean floor through a cable not much thicker than a garden hose, and in some places, thinner. That realization changes the feeling of the internet entirely. Suddenly, it stops feeling abstract. It becomes industrial, physical, vulnerable. More like a railroad system hidden underwater than a magical digital realm. In the 19th century, before fiber optics and cloud computing and smartphones existed, sending information across the Atlantic Ocean was painfully slow. A message leaving Europe for North America still had to travel physically by ship. Storms could delay it for weeks. Governments made decisions using outdated information. Financial markets operated with massive delays. Entire wars unfolded faster than communication itself. In some ways, the speed of civilization was limited by the speed of the ocean. Then a radical idea emerged. What if information could cross the Atlantic instantly? Not carried by ships, but by electricity moving through a wire laid directly beneath the sea. At the time, the proposal sounded almost absurd. The Atlantic Ocean was enormous. Much of its depth was still mysterious. The pressure near the seabed was poorly understood. Engineers barely knew whether a cable could survive the journey, let alone function afterward. Yet in the 1850s, enormous efforts began to lay the first transatlantic telegraph cables between Europe and North America. The process was chaotic from the beginning. Early cables snapped under their own weight. Storms threw ships off course. Signals weakened dramatically across long distances. Financial backers lost fortunes. Some critics believed the entire project bordered on scientific fantasy. But there was also a deeper reason the idea obsessed people. For most of human history, distance controlled power. Oceans separated civilizations not only physically, but informationally. A ruler on one continent could not truly react in real time to events happening on another. The telegraph threatened to collapse that separation for the first time in history. When the first successful transatlantic telegraph messages were finally exchanged in 1858, the world reacted with amazement. Queen Victoria sent a message to President James Buchanan. Newspapers described the achievement almost like a supernatural event. Information had crossed an ocean in minutes instead of weeks. Although the first cable soon failed after excessive voltage damaged it, the psychological shift had already happened. Humanity had seen the future. The ocean no longer seemed like an absolute barrier. It had become a surface beneath which civilization itself could travel. In hindsight, those early submarine telegraph cables were primitive ancestors of today's internet infrastructure. The materials changed. Electricity became light. Copper gave way to fiber optics. But the core idea remained almost identical. Civilization solving distance by placing communication lines beneath the sea. And what is fascinating is how little the public image of the internet reflects this reality. Even now, people often imagine global communication as wireless, because the last few feet of the connection usually are. Your phone talks to a Wi-Fi router wirelessly. The router may connect to a local network underground. That network eventually reaches giant data centers and submarine landing stations, where information is pushed into undersea cables crossing entire oceans. The wireless part is often only the final tiny step in a much larger physical chain. In a sense, modern life feels wireless, mainly because the wires have been hidden. There is something almost poetic about that. The deeper technology integrates into daily life, the more invisible its physical structure becomes. Most people never see the electrical grid behind their lights. They rarely think about pipelines when turning on hot water, and almost nobody pictures seafloor cables while scrolling social media late at night. Yet these systems quietly shape civilization every hour of every day. In some places, submarine cables are so important that entire national economies depend on only a handful of lines connecting them to the rest of the world. When one fails, internet speeds can slow dramatically across entire regions. Financial transactions may reroute through longer paths. Video calls become unstable. Governments and telecommunications companies monitor these networks constantly, because even small disruptions can ripple outward in ways ordinary users never notice directly, but still feel indirectly. And despite the futuristic image of the digital age, many parts of this infrastructure remain surprisingly fragile. Some cables lie in deep regions of the ocean that are relatively undisturbed. Others pass through busy shipping routes where anchors, fishing equipment, or underwater landslides can damage them unexpectedly. Over the years, there have even been occasional reports of sharks biting cables, though experts generally consider human maritime activity a much larger threat than marine life itself. Still, the idea persists because it perfectly captures the strange collision between advanced technology and the ancient unpredictability of the ocean. One side of civilization builds global communication networks using lasers and precision engineering. The other side reminds us that those networks still rest on the floor of a living planet filled with storms, tectonic pressure, corrosion, and darkness. There is another detail that makes submarine cables feel almost unsettling once you realize it. Much of the internet's speed depends not just on technology, but geography. Companies spend billions trying to shorten communication routes by fractions of a second, because even tiny delays can matter in finance, cloud computing, or large-scale data systems. The physical path of a cable across the seabed can influence economic competition itself. In some cases, the shape of the ocean floor quietly affects global markets. And because these cables are so strategically important, they have also become geopolitical concerns. Governments rarely discuss every detail publicly, but many analysts believe submarine communication infrastructure has become increasingly tied to national security planning. Some experts warn about sabotage risks during future conflicts. Others argue that the network's redundancy makes it more resilient than people assume. The truth probably lies somewhere between those extremes. Like many systems built by civilization, the internet appears strongest when everything functions normally. Its hidden complexity only becomes visible during moments of failure. Yet perhaps the most remarkable part of all this is how old the underlying dream really is. Long before streaming platforms or smartphones existed, humans were already obsessed with overcoming distance. The telegraph was one attempt. Radio was another. Satellites expanded the idea further. But the modern internet still depends heavily on a 19th century concept that never truly disappeared. If you want to move enormous amounts of information quickly and reliably across oceans, eventually you may still end up laying a physical line through darkness beneath the sea. And in a strange way, that makes the internet feel less like a futuristic invention and more like the latest chapter in a very old human story. A story about connection, about shrinking the planet, about refusing to let geography fully isolate one part of humanity from another. But laying a cable onto the ocean floor turned out to be only the beginning. Because once humanity realized it could send information beneath the sea, the next challenge became figuring out how to build an entire invisible world down there without letting the ocean destroy it. At first glance, the cables do not look important enough to carry civilization. That may be the strangest detail about them. After hearing that almost the entire modern internet crosses the ocean floor through submarine cables, many people imagine enormous industrial pipelines resting in the deep sea, thick as train tunnels and armored like military machinery. But when sections of these cables are displayed in museums or carried by technicians on docks near landing stations, the reaction is usually the same: disbelief. Some are only about as wide as a garden hose. The actual core carrying the information can be thinner than a human finger. And inside that narrow space flows an endless river of human activity. live streams from Los Angeles, banking transactions from Singapore, emergency calls, scientific research, military communications, late-night arguments. Entire cloud computing systems synchronizing between continents while most of humanity sleeps, without ever realizing how physically delicate the process truly is. The deeper you look into submarine cables, the less the internet feels virtual. It begins to resemble a giant nervous system stretched across the planet, with tiny pulses of light moving beneath oceans in total darkness. And surprisingly, light matters far more than electricity. Modern submarine cables rely primarily on fiber optics, one of the most important technologies ever created for communication. At the center of the cable are strands of glass so pure and precisely engineered that light can travel through them for enormous distances while carrying huge amounts of information encoded into pulses. Not electricity in the traditional sense, light. That idea alone still feels slightly surreal, even after decades of scientific advancement. Somewhere beneath the Pacific Ocean, flashes of laser light are silently transporting conversations between continents faster than any ship in history ever could. The physics behind this system is elegant enough to feel almost unnatural. Light entering a fiber optic strand reflects internally again and again along the glass walls, continuing forward across immense distances without escaping. Engineers call this total internal reflection, but the technical term barely captures how strange it really is. Information is essentially trapped inside glass and guided through the ocean at extraordinary speed. Under ideal conditions, those signals move close to the speed of light itself, slowed slightly by the material of the fiber. And because multiple wavelengths of light can travel simultaneously through a single strand, enormous amounts of data can move at once. Different colors of invisible laser light effectively share the same pathway without colliding, a concept that once sounded so improbable it bordered on science fiction. Yet even this system has limits. Light weakens over long distances. Tiny imperfections inside the fiber gradually reduce signal strength. After traveling across thousands of miles of ocean floor, the pulses become harder to distinguish from background noise, which means submarine cables require another hidden technology most people never hear about: repeaters. These devices sit along the cable at intervals across the seafloor, quietly amplifying the signal so it can continue its journey between continents. Without them, transoceanic fiber communication would collapse. The repeaters themselves are fascinating because they transform the cable from a passive wire into something closer to a living chain of machines stretching across the ocean floor. Some cables contain hundreds of repeaters placed dozens of miles apart. Each one must survive crushing pressure, freezing temperatures, corrosion, and decades underwater without maintenance. In many cases, engineers design them to operate continuously for 25 years or more. That level of reliability feels almost impossible when you consider where they are located. Human beings cannot casually visit these systems for repairs. Once the cable sinks into the deep ocean, it enters an environment that remains hostile even to advanced submarines. The pressure alone in some abyssal regions would crush ordinary equipment instantly, which means every component inside a submarine cable must work correctly for years while isolated in darkness beneath miles of water. And despite the futuristic image of the internet, the cables themselves contain surprisingly old-fashioned physical layers. Around the fiber optic core are protective materials designed not for data, but survival. Gel compounds help block water intrusion. Copper layers conduct electrical power through the cable to feed the repeaters. Steel armor protects vulnerable sections from external damage. Near coastlines, where anchors and fishing equipment pose serious risks, cables may receive additional layers of reinforcement that make them dramatically thicker than the sections lying undisturbed in the deep ocean. In some shallow regions, engineers even bury the cables beneath the seabed for protection. Farther offshore, however, many cables simply rest directly on the ocean floor. That image feels strangely vulnerable once you understand it clearly. Civilization's communication system lying quietly across mud, rock, volcanic ridges, and deep underwater plains, while invisible currents move above it. One of the most counterintuitive aspects of submarine cables is that they are not primarily powered by local energy sources scattered across the ocean floor. Instead, enormous amounts of electricity are sent through the cable itself from stations located on land. Some systems operate with thousands of volts running continuously across entire oceans to power the repeaters along the route. The engineering challenge here is remarkable because the system must remain electrically stable across distances that can exceed thousands of miles underwater. Any significant failure becomes extremely difficult to repair, and unlike many ordinary machines, submarine cables cannot simply shut down temporarily without consequences. The modern world depends too heavily on constant connectivity. There is something almost unsettling about how much trust civilization places in these thin lines. Financial markets respond in milliseconds to information crossing oceans. Cloud computing systems constantly synchronize enormous amounts of data between continents. Governments exchange intelligence through networks routed beneath the sea. Even artificial intelligence systems increasingly rely on globally distributed infrastructure connected through submarine cables. In some ways, the cables themselves have become more important than many people realize, because they form the hidden foundation underneath technologies that attract far more public attention. Satellites may dominate headlines because they are visible and dramatic, but submarine cables quietly carry far more of the world's actual internet traffic. That imbalance between visibility and importance appears repeatedly throughout modern civilization. The systems that matter most are often the least noticed. There is also an interesting geographical logic hidden inside global cable networks. Not every route is equally valuable. Certain coastlines became communication hubs because they provide efficient pathways between continents. Some regions developed dense clusters of cables, while others remained comparatively isolated. The shape of the ocean floor, political stability, proximity to data centers, and historical trade patterns all influenced where cables were eventually placed. In some cases, today's digital infrastructure still echoes roots shaped by older systems of empire, shipping, and commerce. The internet often feels new, but parts of its physical geography are rooted in centuries-old patterns of global connection. At the same time, submarine cable maps reveal how concentrated global communication can become. Certain choke points carry enormous amounts of data through relatively narrow regions. Areas near Egypt, the Strait of Malacca and parts of the Mediterranean became especially important because multiple cable routes converge there. Analysts sometimes debate how resilient these networks truly are. Supporters point out that modern internet infrastructure contains significant redundancy, allowing traffic to reroute around damaged cables in many cases. Critics argue that increasing dependence on cloud computing and globalized systems may create vulnerabilities that remain poorly understood until disruptions occur. Neither interpretation is entirely unreasonable. The truth is likely more complicated than either extreme. What is clear is that submarine cables transformed oceans from barriers into information corridors. And perhaps the most fascinating part is how ordinary the cables can appear, despite their importance. Workers handling sections on ships or at landing stations often describe them almost casually because, from a physical perspective, they really are just cables, long engineered objects made of glass, metal, insulation, and protective layers. Yet their simplicity hides extraordinary consequences. A single cable can carry communications for millions of people simultaneously. It can influence financial systems, emergency response coordination, scientific collaboration, entertainment industries, and geopolitical relationships all at once. In another era, civilizations measured power through roads, ports, canals, or railways. Modern civilization increasingly measures it through data infrastructure. And under the oceans, that infrastructure often narrows into fragile strands lying silently in darkness. There is another detail that makes submarine cables feel strangely beautiful once you think about them long enough. They transform the ocean into a place filled with invisible motion. On the surface, the sea may appear calm and empty beneath moonlight. But deep below, countless streams of human thought are racing through glass fibers at extraordinary speed. Entire digital worlds crossing beneath whales, volcanic ridges, and drifting sediment. It creates an almost eerie contrast between ancient nature and modern civilization. One system shaped by geology and planetary time, the other shaped by human urgency, communication, and constant demand for connection. And despite all the engineering involved, the cables themselves remain surprisingly vulnerable. Near coastlines, they face anchors, fishing trawlers, and accidental damage. In deeper regions, underwater landslides and tectonic activity become concerns. Engineers attempt to reduce these risks through careful planning and protective design, but there is no perfect solution because the ocean itself is unpredictable, which means every functioning cable represents an ongoing negotiation between technology and the environment surrounding it, a negotiation happening mostly out of public sight. And perhaps that hidden quality is why submarine cables feel so compelling once discovered. They reveal that the internet is not an abstract cloud detached from reality. It is a physical machine built inside the real world, exposed to weather, pressure, geography, economics, politics, and time. The digital age did not eliminate physical infrastructure. It buried it beneath the sea, where most people would never think to look. But building the cables themselves was still only part of the challenge. Because even after humanity learned how to construct these delicate arteries of light, someone still had to carry them across entire oceans and lower them carefully into the darkness below. Long before a submarine cable ever touches the ocean floor, it begins its journey inside a ship that feels less like a normal vessel and more like a floating industrial organism built for one highly specific purpose. From the outside, cable-laying ships can appear strangely ordinary at first glance. Large hulls, communication towers, deck machinery. Nothing about them immediately suggests that they are carrying pieces of the global internet inside their steel bodies. But once you step deeper into the ship, the scale of the operation becomes difficult to forget. Beneath the deck are enormous circular tanks filled with tightly coiled submarine cable, layer upon layer, stacked with extraordinary precision, sometimes hundreds or even thousands of miles of it, spiraling downward into vast compartments that resemble giant underground labyrinths. Workers moving through these chambers often look tiny beside the endless loops of cable surrounding them. And in a way, they are standing inside a future communication network before it even exists. Because once the ship leaves port, those coils will slowly unroll across entire oceans, eventually becoming the invisible pathways connecting continents. There is something oddly cinematic about the process, because the mission itself unfolds with almost no public attention, despite influencing millions of lives. Cruise ships carry tourists. Aircraft carriers project military power. Cargo ships move visible goods. But cable-laying ships quietly transport information infrastructure, one of the most important resources of the modern world, without most people ever noticing they exist. And unlike many industrial operations, this work cannot rely on brute force alone. Submarine cable deployment demands patience, precision, and constant adjustment because the ocean rarely behaves predictably for long. A single major cable project can take months to complete. Engineers, navigators, marine specialists, technicians, and sailors may spend long stretches isolated at sea, while the ship moves at surprisingly slow speeds across enormous distances. In some situations, the vessel advances only a few miles per hour, while carefully feeding cable into the water behind it. That slow movement feels almost contradictory to the internet itself. Modern digital culture revolves around speed. Instant downloads, instant replies, instant access. Yet the infrastructure supporting all of it is often built through painfully gradual physical labor happening far from public view. There is no rushing the ocean. Every movement must be controlled. Every section of cable must leave the vessel under carefully managed tension. Too much force and the cable may snap under stress. Too little control and loops or twists can form during deployment, potentially damaging the system before it even becomes operational. The margins for error become especially dangerous in deep water because once the cable descends thousands of meters into darkness, recovering it is extremely difficult. In some cases, a mistake made in seconds could require weeks of repair work and enormous financial losses. That pressure creates a strange atmosphere on board these ships. The work is technical, but it also carries the emotional intensity of high-risk navigation. Crews constantly monitor weather, ocean currents, cable tension, seabed conditions, and ship positioning at the same time. Dynamic positioning systems use thrusters and satellite navigation to keep the vessel precisely aligned along its planned route, sometimes with astonishing accuracy considering the conditions involved. Modern cable ships can hold position within meters even while operating in open ocean environments where waves, wind, and currents continuously push against them. Earlier generations of cable ships lacked many of these advanced systems, making the process far more dangerous and uncertain. In the 19th century, laying submarine telegraph cables often bordered on chaos. Ships struggled with navigation errors, storms disrupted deployment, cables snapped and vanished into deep water. Entire missions failed after months of work. Some historians argue that early submarine cable engineering was among the most ambitious technological projects of the industrial era, precisely because so much of the ocean remained poorly understood at the time. Engineers were attempting to build communication systems inside an environment humanity could barely observe directly. In some ways, modern cable operations still carry traces of that uncertainty. Even today, the deep ocean remains difficult to study comprehensively. Weather forecasts improve, sonar mapping advances, satellite navigation increases precision. Yet, the sea still introduces variables no simulation fully controls. Storm systems can force deployment delays. Unexpected seabed conditions may require route changes. Mechanical failures on board the vessel itself can create enormous complications because the entire mission depends on maintaining a continuous, controlled process. And unlike many construction projects on land, there are no nearby roads, supply depots, or emergency repair crews waiting just beyond the horizon. Out in the open ocean, the ship becomes its own isolated world. Inside the cable tanks, workers must handle the enormous coils with extreme care. The cable cannot simply be dumped into storage randomly because deployment depends on maintaining precise organization. Each section is loaded strategically so it feeds out smoothly during the voyage. Some modern submarine cables weigh thousands of tons in total. Watching them disappear steadily into the ocean creates a strangely hypnotic image. The ship moves forward almost silently, while the cable slides downward through guide systems at the stern, vanishing beneath dark water toward terrain no human eye may ever directly see. There are moments during deployment when the operation begins to resemble surgery more than construction. Engineers monitor data constantly, adjusting tension and speed in response to ocean depth changes. If the seabed suddenly drops into a deep trench, the cable's descent angle changes dramatically. If underwater terrain becomes rough or unstable, crews may alter deployment patterns to reduce stress on the line. Some regions require extra slack to account for geological movement or future environmental shifts. The goal is not simply to place the cable, but to place it in a way that allows it to survive for decades beneath one of the harshest environments on Earth. Near coastlines, the process becomes even more delicate. Shallow waters are often the most dangerous part of the route because human activity increases dramatically there. Fishing operations, shipping traffic, anchors, dredging equipment, and coastal construction all create potential threats. In these areas, Additional vessels may assist the operation, while divers or remotely operated vehicles help guide and protect the cable during placement. Specialized underwater plows sometimes bury the cable beneath the seabed to shield it from future damage. Watching footage of these machines moving slowly across the ocean floor feels strangely surreal because it reveals how physical and mechanical the internet truly is. Beneath beaches and harbors where tourists walk without thinking about global infrastructure, robots are literally carving trenches for communication lines beneath the sea. There is also a financial intensity surrounding cable missions that adds another layer of pressure. Large submarine cable systems can cost hundreds of millions or even billions of dollars, depending on route complexity and scale. Delays caused by storms or technical failures become extremely expensive very quickly. Every day at sea matters. Every operational mistake carries consequences. Yet, despite these risks, the demand for new cables continues growing because global data consumption keeps accelerating. Streaming platforms, cloud computing, artificial intelligence, financial systems, and international communications all require increasing bandwidth between continents. In a sense, cable ships are constantly chasing civilization's appetite for information, and that appetite rarely slows down for long. Some analysts even argue that submarine cable infrastructure may become more strategically important over time rather than less. For years, many people assumed satellites would eventually replace large portions of undersea communication systems. But while satellite technology continues advancing rapidly, especially with low Earth orbit networks, submarine cables still offer major advantages in bandwidth capacity, stability, and latency for large-scale internet traffic. It is possible the future will involve a hybrid system where satellites expand coverage while submarine cables remain the primary arteries of global data transfer. But for now, the oceans still carry most of the digital world beneath their surface. There is something deeply human about the entire process. Despite all the advanced technology involved, submarine cable deployment still depends heavily on people working carefully in uncertain conditions, engineers interpreting data, crews responding to changing seas, navigators adjusting routes, technicians monitoring systems hour after hour through long shifts, while the ship moves slowly across enormous, empty distances. The internet often feels automated from the perspective of ordinary users, yet beneath that illusion is an immense amount of physical labor and coordination happening continuously around the planet. And perhaps that hidden labor explains why cable ships feel almost symbolic of modern civilization itself. Quiet systems operating mostly unseen, carrying structures that millions depend on without fully understanding. At night, the atmosphere on board can become strangely calm despite the pressure of the work. Outside the vessel, the ocean stretches into darkness, beneath stars and radar signals. Inside, machinery hums while operators watch tension readings and route data glowing softly across screens. Somewhere below the hull, another section of cable slips into black water, beginning a descent toward the sea floor that may take hours before it finally settles into place. Eventually, that line will become part of everyday life for people who will never know the ship existed. A teenager streaming music in California, a hospital transferring medical data between countries, a business call crossing the Atlantic in fractions of a second. Entire pieces of civilization quietly depending on decisions made by crews drifting through the ocean months or years earlier. Yet, even with all this technology and planning, one problem still remained before any cable could be safely placed. Because lowering the internet into the sea required something humanity still did not fully possess for much of history: a reliable understanding of what was actually waiting at the bottom of the ocean. For most of human history, the bottom of the ocean was less a place than an absence, a hidden world beneath ships and storms where almost nobody could see, measure, or survive for long. Sailors crossed oceans without truly knowing what existed below them. Ancient maps filled the unknown with sea monsters and giant voids. And in a strange way, those myths were not entirely irrational. The deep ocean really was one of the least understood environments on Earth. Even now, after satellites, nuclear submarines, and global internet networks, large portions of the seafloor remain mapped in surprisingly low detail compared to the surface of the Moon or Mars. That fact feels almost backwards at first. Humanity can photograph distant galaxies billions of light years away, yet parts of our own planet remain shadowed beneath waters so deep and inaccessible that no human eye has ever directly observed them. And before a submarine cable can safely cross an ocean, someone first has to understand that darkness well enough to guide civilization through it. Long before cable ships begin laying fiber across the seabed, another process begins quietly in advance. Survey missions, mapping operations, years of studying terrain hidden beneath miles of water. Because placing a cable blindly across the ocean would be catastrophic. The sea floor is not flat. It is a landscape, violent in some places, fragile in others. Entire mountain ranges rise beneath the Atlantic and Pacific Oceans. Underwater volcanoes slowly reshape terrain over geological time. Vast trenches descend deeper than Mount Everest is tall. Some regions are covered in soft sediment, while others contain jagged rock formations capable of damaging infrastructure under pressure and movement. And, unlike roads on land, submarine cables cannot simply be inspected easily after installation. The route must be understood before deployment begins. Modern survey vessels use sonar systems to map the seabed in remarkable detail. Sound pulses travel downward through dark water, bouncing back toward receivers that convert echoes into topographic images. In a sense, humans learn to see the deep ocean by listening to it. That detail feels strangely fitting because the ocean itself absorbs light rapidly. Only sound travels efficiently through such enormous underwater distances. During mapping operations, survey ships slowly cross future cable routes, while computers build digital terrain models beneath them. The resulting images can reveal underwater ridges, slopes, sediment patterns, wrecks, volcanic structures, and geological hazards invisible from the surface. Watching modern sonar maps emerge can feel almost like uncovering another planet hidden beneath Earth's oceans. Some areas appear smooth and calm, Others look chaotic, scarred by tectonic movement and underwater landslides. Engineers must interpret all of it carefully, because the wrong route can destroy a cable years later. One of the greatest threats comes from geological instability. Earthquakes beneath the ocean floor may trigger underwater avalanches powerful enough to damage communication lines across large regions. In some historical cases, scientists studying broken submarine cables were able to reconstruct the timing and movement of massive underwater sediment flows after earthquakes occurred. The cables unintentionally became geological witnesses, recording disturbances moving through darkness beneath the sea. That overlap between communication infrastructure and earth science is fascinating because it reveals how closely modern technology has become intertwined with planetary systems. The internet does not float above nature. It exists inside it. And nature continues operating according to its own rules, regardless of how advanced human civilization becomes. Route planners therefore avoid certain regions whenever possible. Areas with heavy tectonic activity, unstable slopes, or volcanic risk may force cables into longer pathways across supposedly safer terrain. But safety itself is relative because no ocean route is entirely predictable over decades. The seabed changes slowly, currents shift sediment, geological stress accumulates invisibly. Some experts believe climate change could eventually influence certain underwater conditions in ways not yet fully understood, though the scale of those effects remains debated. What is clear is that cable planning requires thinking not only about present geography, but future uncertainty, and that uncertainty grows larger the farther humans move from shore. Near coastlines, there are at least ships, ports, and regular activity. Far offshore, the deep ocean becomes increasingly alien. Temperatures approach freezing. Sunlight disappears completely. Pressure rises to crushing levels. In some abyssal regions, the environment changes so slowly that disturbances may remain visible for years. It is easy to imagine the deep sea as chaotic because the ocean surface appears constantly in motion. But many deep ocean plains are eerily still compared to coastal waters. That quietness is actually one reason submarine cables often survive successfully once placed in stable deep water areas. Ironically, some of the safest places for internet infrastructure are among the most remote and lifeless environments on Earth. Yet reaching those places safely requires extraordinary planning. Survey teams study not only geology, but also human activity. Shipping lanes matter enormously because anchors remain one of the most common causes of cable damage. Fishing zones introduce additional risks from trawling equipment dragging across the seabed. In shallow waters near busy coastlines, cables may need burial beneath sediment for protection. Military zones, offshore energy infrastructure, protected ecosystems, and international territorial boundaries can all influence route selection as well. By the time a cable route is finalized, it reflects not just engineering decisions, but economics, politics, environmental concerns, and strategic calculations layered together beneath the ocean surface. Some submarine cable routes are publicly known in broad terms, but exact details are sometimes treated carefully. Partly for security reasons, partly for commercial competition, and partly because these networks became increasingly important to national infrastructure over time. Governments understand that modern economies rely heavily on stable international communication. Financial systems, cloud computing, military coordination, scientific collaboration, emergency response networks, and global business operations all depend on undersea cables functioning continuously. That dependence inevitably attracts geopolitical attention. In recent years, analysts and defense officials from multiple countries have expressed growing concern about the vulnerability of submarine communication infrastructure during future conflicts or periods of international tension. Some warnings may be exaggerated for political effect. Others may reflect legitimate strategic concerns. The reality is difficult for outsiders to evaluate fully because much of the discussion happens quietly behind governments and private corporations. But the fact that submarine cables now appear in geopolitical conversations at all reveals how important they have become. In some ways, the modern world rests on infrastructure most citizens never think about until something goes wrong. There is also an eerie historical symmetry in the geography of submarine cables. Many modern routes echo pathways shaped by older systems of trade and empire. Communication corridors often follow coastlines and choke points that were strategically important centuries before the internet existed. The Mediterranean remains critical. So do passages near Egypt and Southeast Asia. Digital civilization inherited part of its geography from older maritime worlds built around shipping and commerce. The technologies changed, but the planet itself still influences where connection becomes concentrated. Some researchers even argue that future geopolitical competition may increasingly involve infrastructure control rather than direct territorial conquest. Data routes, energy systems, satellite networks, and communication choke points could become more strategically significant than many people currently realize. Whether those predictions prove accurate remains uncertain, but submarine cables clearly occupy a strange position between civilian technology and national infrastructure. They are commercial systems carrying ordinary internet traffic, yet they also underpin governments, militaries, and economies simultaneously. That dual role makes them difficult to classify neatly. And beneath all the strategic planning and engineering is still the unsettling reality that much of the deep ocean remains poorly explored. Despite decades of mapping improvements, scientists estimate that only a fraction of the global seafloor has been mapped at high resolution. Some estimates vary depending on what counts as detailed mapping, but the broader point remains true. Humanity still knows surprisingly little about vast portions of its own planet. That ignorance creates a strange emotional atmosphere around submarine cable infrastructure. Engineers are building one of the most advanced communication systems in human history across terrain that remains partly mysterious. In another era, laying cables beneath unknown oceans might have been described as conquering nature. Today, it feels more complicated than that. Humans are not conquering the ocean so much as negotiating temporary pathways through it. Every route represents compromise with geography, geology, and uncertainty. And the ocean never truly stops changing. Sometimes survey missions uncover unexpected things: shipwrecks, geological formations, unusual sediment patterns. In rare cases, previously unmapped features large enough to alter planning decisions entirely. The seafloor preserves layers of history invisible from the surface: ancient volcanic activity, tectonic scars, human wreckage, lost aircraft, Cold War debris. The internet itself now joins that hidden archaeological landscape, lying quietly beside remnants of older civilizations and disasters beneath the water. There is something deeply strange about that image. Humanity's newest communication systems resting among the forgotten remains of previous eras in total darkness. And perhaps that darkness is part of why submarine cables feel so psychologically fascinating once people discover them. They expose a hidden layer of modern civilization operating beneath ordinary awareness. Every message, live stream, search query, and cloud backup traveling through a physical system stretched across terrain most humans will never see directly. The digital world suddenly stops feeling weightless. It gains geography, pressure, vulnerability, distance. The internet becomes not a magical cloud, but a machine laid carefully through one of the least understood places on Earth. And after years of mapping, surveying, and planning, there eventually comes a moment when theory ends and risk begins. Because understanding the seabed is one thing, lowering the cable into that darkness for the first time is something else entirely. There is a moment during submarine cable deployment when the internet stops being an engineering plan and begins becoming part of the Earth itself. It happens quietly. No dramatic countdown, no public audience watching from beaches. Usually just a group of engineers and crew members standing beneath gray skies while machinery hums across the deck of a cable ship drifting slowly offshore. The cable moves steadily through tension wheels toward the stern of the vessel, disappearing inch by inch into dark water behind the ship. And once that descent begins, the atmosphere changes. Because unlike many construction projects, submarine cable deployment allows almost no room for improvisation after the process is underway. The ocean does not forgive mistakes easily. A modern submarine cable may eventually stretch thousands of miles across entire oceans, but every route begins with this fragile transition point where human control slowly gives way to gravity, pressure, current, and darkness. The cable leaves the ship and starts sinking toward terrain nobody on board can directly see. In shallow coastal regions, that descent may only take minutes. In deep ocean environments, parts of the cable may fall through cold black water for hours before finally touching the seabed. And throughout the entire process, crews must maintain extraordinary precision because the cable itself is under constant physical stress. Too much tension and it could snap under its own weight. Too little control and loops may form on the seabed, increasing future vulnerability or damaging the system entirely. The deeper the water becomes, the more difficult the mathematics grow. Every shift in depth changes the angle and behavior of the descending cable. Ocean currents push against it invisibly. The moving ship alters the geometry continuously. Engineers on board monitor streams of live data while adjusting deployment speed in real time, trying to maintain a balance between the cable, the vessel, and the unseen terrain waiting below. Watching the process unfold can feel strangely hypnotic, because so much depends on movements that appear almost slow and uneventful from the surface. Yet beneath the water, gravity is pulling miles of delicate infrastructure into one of the harshest environments on Earth. Some crew members who worked on cable ships have described the process less like construction and more like guiding something alive. Not because the cable itself moves independently, but because the entire system constantly reacts to conditions. The ship cannot simply drag the cable behind it carelessly. Every section must settle properly across underwater terrain that may rise, slope, or fracture unexpectedly. In some areas, additional slack is intentionally introduced to reduce stress over uneven ground. In others, crews must avoid placing too much loose cable where movement or currents could eventually create dangerous tension points. Even after years of route surveys and planning, the final deployment still contains uncertainty because the ocean never becomes entirely predictable. Near coastlines, the operation becomes especially tense. Ironically, shallow water is often more dangerous than the deep ocean itself. Human activity increases dramatically closer to land. Fishing vessels move constantly through coastal regions. Cargo ships cross busy routes. Anchors scrape seabeds. Construction projects disturb sediment. The cable, therefore, requires additional protection during its earliest stage underwater. Specialized vessels sometimes assist near shore, while divers or remotely operated vehicles monitor placement. In many modern installations, giant underwater plows are used to carve trenches into the seabed so the cable can be buried beneath sediment. Footage from these operations feels almost surreal because it reveals an invisible layer of civilization hidden directly beneath ordinary coastlines. Tourists walk along beaches while, somewhere offshore, robotic machinery slowly buries the physical infrastructure carrying global communication beneath the sand. The deeper offshore the cable travels, the stranger the environment becomes. Sunlight disappears rapidly underwater. Within a few hundred meters, darkness dominates completely. Temperatures approach freezing. Pressure rises with astonishing speed. At depths of several thousand meters, the weight of the ocean above becomes almost difficult to comprehend intuitively. Yet the cable continues descending steadily into that darkness, guided only by calculations, sensors, and experience. There is something psychologically unsettling about this phase of deployment, because humans remain almost entirely separated from the environment where the infrastructure will spend most of its existence. Astronauts at least see space directly through windows. Deep ocean cable deployment often occurs into a world invisible from the surface. The crew knows where the cable should land, but they cannot watch it happen in real time with their own eyes. In some situations, remotely operated underwater vehicles later inspect sections of the route using cameras and sonar systems, revealing eerie images of the cable resting silently across mud plains or rocky slopes under absolute darkness. Those images have a strange emotional quality. The internet suddenly appears physical and lonely, lying quietly beneath thousands of feet of water, while invisible streams of human communication race through glass fibers inside it. And despite all the precision involved, cable deployment still contains moments of genuine danger. Storms remain one of the greatest threats. A cable ship moving slowly during deployment cannot maneuver as freely as ordinary vessels. Heavy seas may force operations to pause entirely because violent movement risks damaging the cable or disrupting placement accuracy. Some crews have spent days waiting for weather windows, while expensive equipment and schedules remain suspended in uncertainty. The financial pressure during these moments can become enormous. Large submarine cable projects cost extraordinary amounts of money, and delays at sea rapidly increase operational expenses. Yet, rushing the deployment is not an option. The cable must survive for decades once it reaches the seabed. A mistake hidden beneath the ocean today may become a catastrophic failure years later. That long-term perspective shapes nearly every decision during installation. Engineers are not simply trying to complete the route quickly. They are trying to place infrastructure capable of operating continuously in darkness for 25 years or more. In some ways, submarine cable deployment resembles sending a machine into space. Once it leaves human reach, reliability becomes everything. There is also a fascinating contrast between the incredible complexity of the internet and the simplicity of what physically enters the ocean during deployment. No glowing futuristic device descends beneath the waves. No giant supercomputer sinks into the abyss. Just a cable, a long engineered line made of glass, steel, insulation, and protective materials, slowly disappearing into black water behind a moving ship. Yet inside that cable is the capacity to carry enormous portions of human civilization's communication. Financial markets, streaming platforms, medical systems, military coordination, artificial intelligence networks, scientific research, family conversations. Entire modern economies increasingly depend on these quiet deployments happening far offshore with almost no public awareness. In another era, civilizations built monuments above ground to symbolize power. Modern civilization often hides its most important structures where almost nobody sees them. The deeper the cable descends, the more symbolic the process begins to feel. Human thought itself is being lowered into darkness. Entire continents connected through lines resting silently across terrain older than human civilization. In some regions, cables cross volcanic ridges slowly formed by tectonic movement over millions of years. In others, they pass through sediment plains so still and isolated that disturbances may remain visible for decades. The timescales collide strangely beneath the sea, geological processes unfolding over planetary history intersecting with internet traffic moving in milliseconds. There is also a persistent illusion surrounding the internet that becomes impossible to maintain once you understand cable deployment clearly. Modern digital culture encourages the feeling that information exists everywhere at once, detached from geography and material limits. But submarine cables reveal the opposite. The internet depends profoundly on geography. Specific routes matter. Coastlines matter. Ocean depth matters. Political boundaries matter. Physical distance still matters, even in the digital age. Because information ultimately travels through real systems embedded in the real world. And nowhere does that reality become more visible than during deployment itself. Every meter of cable placed on the seabed represents physical labor overcoming physical distance. Some analysts argue that this hidden infrastructure may become even more important in the future, as cloud computing and artificial intelligence continue expanding globally. Data demands increase constantly. Entire industries now rely on rapid international communication. New cables are continuously planned because older systems eventually reach capacity or require redundancy. In a sense, humanity is quietly weaving an increasingly dense communication layer across the oceans, a second invisible geography forming beneath the natural one. And yet, despite all the planning and technology, the deployment phase never entirely escapes uncertainty. Ocean currents shift unexpectedly. Equipment fails. Weather changes. Mechanical stress behaves unpredictably under certain conditions. There are moments during deployment when engineers must make judgment calls based partly on experience, because not every variable can be perfectly modeled. That human element remains surprisingly important. Civilization often imagines modern infrastructure as fully automated, but submarine cable deployment still depends heavily on crews interpreting conditions in real time while operating far from immediate assistance. At night, the atmosphere aboard cable ships can become strangely quiet during deployment operations. Beyond the deck lights, the ocean disappears into darkness. Machinery continues feeding cable steadily into the sea while monitors glow inside control rooms. Somewhere far below, another section of the internet is descending through freezing black water toward terrain no human being may ever directly touch. Eventually, it will settle into place and remain there for decades, while millions of people use systems built upon it without ever knowing the route exists. Yet, the most unsettling part of all may be this. Once the cable finally disappears beneath the surface, civilization must trust that the ocean will leave it alone. But the ocean rarely stays quiet forever. For something so important, the global internet survives in surprisingly fragile conditions. That realization becomes difficult to ignore once you understand where submarine cables actually live. Thousands of miles of communication infrastructure resting across dark seafloors beneath storms, shipping routes, tectonic fault zones, and one of the least predictable environments on Earth. And despite the futuristic image often attached to the internet, many of the greatest dangers threatening it are strangely primitive. Metal scraping against the seabed, geological violence deep beneath the ocean floor, human error, heavy objects falling in the wrong place at the wrong time. There is a tendency to imagine cyber threats as invisible code moving through computers. But some of the most serious internet disruptions in history began with physical damage in the real world. A cable breaks somewhere underwater, and suddenly entire regions feel the consequences, without most people understanding why. The strange thing is that the most famous threat is probably not the most dangerous one. Sharks became linked to submarine cables partly because there have been documented incidents of sharks biting undersea communication lines. Early engineers noticed tooth marks on damaged cables decades ago, and modern examples occasionally appear in headlines whenever footage surfaces of sharks interacting with underwater infrastructure. Some theories suggest electromagnetic fields emitted by cables may resemble signals certain shark species use to sense prey. Other researchers believe curiosity may play a larger role than attraction. The exact explanation remains debated in some cases. and experts generally agree that shark damage represents a relatively minor problem compared to human maritime activity. But the idea persists because it perfectly captures the unsettling feeling of modern civilization resting inside a living ocean that does not fully care about human systems. The image itself is difficult to forget. Ancient predators drifting through darkness beside the cables carrying humanity's digital world. Yet in reality, the greatest threat usually comes from ships, especially near coastlines. Anchors remain one of the leading causes of submarine cable damage worldwide. A heavy anchor dragged across the seabed can hook, crush, or sever cables with astonishing force. Fishing trawlers create similar risks. Large nets and dragging equipment scrape ocean floors constantly in busy maritime regions, sometimes catching cables unintentionally. That danger explains why coastal sections are often heavily armored or buried beneath sediment using specialized underwater plows. Engineers know the most vulnerable parts of the network are often not the deep abyssal plains, but the crowded shallows where human activity never truly stops. There is something almost ironic about that pattern. The deepest parts of the ocean may appear more frightening psychologically, yet many cables survive there relatively undisturbed for years because so little reaches them. Closer to civilization, however, the danger increases dramatically. Human movement itself becomes the threat. In some regions, shipping traffic grows so dense that submarine cable maps resemble transportation arteries beneath the sea. Certain coastal bottlenecks carry enormous amounts of global communication through relatively narrow spaces. Damage in those zones can ripple outward far beyond local waters. Over the years, there have been multiple incidents where broken cables significantly slowed internet connectivity across entire countries or regions. In 2008, a series of submarine cable disruptions near the Mediterranean and Middle East affected internet performance across several nations, creating noticeable slowdowns and communication issues. Similar events have occurred near Southeast Asia, Africa, and other heavily connected regions. Often, the public experiences these disruptions simply as slow internet, without realizing that somewhere beneath the ocean floor, a physical communication line has been damaged. That disconnect between everyday experience and hidden infrastructure feels deeply characteristic of the digital age. Civilization depends on systems most people never see directly. The failure becomes visible long before the machinery behind it does. Some submarine cable routes became so strategically important that analysts now refer to them almost like maritime choke points for information. Areas near the Red Sea, the Suez region, the Strait of Malacca, and parts of the Mediterranean carry immense quantities of global data traffic because geography funnels routes through those corridors. The concentration creates efficiency, but also vulnerability. If several cables in the same region fail simultaneously, rerouting traffic becomes far more difficult. Modern internet systems are designed with redundancy, meaning information can often travel alternative pathways when damage occurs. But redundancy itself has limits depending on location and traffic demand. Some experts argue the global network remains more resilient than public discussions sometimes imply. Others warn that increasing dependence on cloud infrastructure and AI systems may intensify pressure on critical routes over time. both perspectives contain some truth.
The internet was designed to survive partial failure, but no infrastructure system becomes infinitely immune to disruption. Nature introduces another layer of unpredictability beneath the sea. Earthquakes can trigger submarine landslides capable of damaging multiple cables in sequence. Unlike dramatic Hollywood depictions of underwater destruction, these events often happen invisibly, in darkness, far below the surface. Sediment shifts violently across the seabed, carrying enormous force through deep water terrain. In some historical cases, scientists reconstructed underwater landslides by studying the timing of cable failures along the ocean floor. One cable breaks, then another farther downhill moments later, almost like dominoes falling beneath the sea. The cables unintentionally became instruments recording geological violence inside environments humans could not directly observe. That overlap between earth science and communication infrastructure remains fascinating because it reveals how deeply modern civilization now depends on planetary stability itself. Every live stream, online payment, cloud backup, and international message ultimately exists inside a physical environment shaped by tectonic pressure, erosion, currents, and weather. Even volcanic activity occasionally enters the conversation. Underwater volcanoes and tectonic spreading zones influence route planning because certain parts of the seafloor remain geologically active over long timescales. Engineers attempt to avoid unstable regions whenever possible, but the Earth is not static. Ocean floors slowly move. Pressure accumulates invisibly. Sediment migrates. In another era, these processes unfolded mostly beyond human concern. Today, they interact directly with communication systems carrying the daily functions of civilization. There are also stranger incidents scattered through submarine cable history. Shipwrecks damaging infrastructure accidentally, fishing equipment pulling up sections unexpectedly, wartime sabotage concerns, accidental cuts during marine construction projects. Even simple human misunderstanding has occasionally caused serious problems. In one reported incident from years ago, fishermen reportedly recovered pieces of submarine cable and attempted to salvage them as scrap metal without fully realizing what they had found. Stories like these reveal how physically ordinary submarine cables can appear, despite their enormous importance. From a distance, they are not obviously part of the global internet. They look more like industrial material than civilization's nervous system. And perhaps that invisibility contributes to their vulnerability. People protect what they recognize as valuable. Hidden infrastructure often receives attention only after failure occurs. Military and intelligence communities also pay close attention to submarine cables, though public information remains limited in many areas. Throughout the Cold War, governments became increasingly aware that undersea communication infrastructure could hold strategic significance. Some reports and declassified operations suggest submarine cables were occasionally monitored or targeted for intelligence purposes. Modern analysts continue debating how vulnerable these systems might be during future geopolitical tensions. Some experts warn about sabotage scenarios involving critical infrastructure attacks. Others argue that fears are sometimes exaggerated because global communication networks contain more redundancy than sensational headlines imply. The truth likely depends heavily on specific regions and circumstances. What is clear is that submarine cables are no longer viewed as merely commercial utilities.
They became part of national infrastructure discussions because modern economies depend on them so heavily. Yet despite all these risks, the system works remarkably well most of the time. That may actually be the most astonishing part. Thousands of cables operate continuously beneath the oceans while carrying enormous amounts of global communication every second. Failures occur, but complete collapse remains rare because the network evolved with resilience in mind. Multiple routes connect major regions. Traffic reroutes dynamically. Engineers monitor systems constantly. Repair ships remain prepared to respond when necessary. Civilization quietly built layers of redundancy beneath the sea because the cost of losing connection became too high to ignore. Still, the balance remains uneasy. Every functioning cable represents a temporary agreement between technology and forces humans never fully control. Storms continue crossing oceans. Anchors continue dropping into water. Earthquakes continue reshaping seabeds. Ships continue moving across trade routes above invisible infrastructure. And all the while, billions of people continue using the internet as though it were weightless and permanent. There is something psychologically strange about realizing how physical the digital world truly is. The internet often feels detached from nature, almost separate from geography and material reality. But submarine cables expose the illusion. The modern world rests on metal, glass, electricity, ships, coastlines, and geological stability. It depends on engineers calculating tension beneath storms, on crews burying cables beneath seabeds, on tectonic plates remaining still enough for communication lines to survive another year. In another century, people feared storms destroying fleets carrying physical letters between continents. Today, humanity fears disruptions to invisible pulses of light beneath the same oceans. The technology evolved, but the dependence on fragile pathways across the planet never disappeared. And when those pathways fail, civilization suddenly remembers they exist. But perhaps the most difficult part comes afterward, because locating a damaged cable beneath thousands of feet of dark ocean is only the beginning. Repairing it is something else entirely. When a submarine cable fails somewhere beneath the ocean, the first thing most people notice is not panic. It is slowness, videos buffering longer than usual, calls dropping unexpectedly, websites loading in strange bursts. Sometimes, entire regions experience dramatic disruptions. Other times, the internet simply feels heavy, as if information itself suddenly became tired crossing the planet. Behind the scenes, network systems begin rerouting traffic almost immediately, trying to push data through alternative pathways, while engineers search for the source of the problem. And somewhere deep beneath the ocean, in darkness colder than most people can imagine, part of civilization's nervous system has gone silent. Finding the exact location of the failure is the first challenge. Surprisingly, engineers can often narrow down the break with remarkable accuracy long before anyone reaches the site physically. Because light moving through fiber optic cables behaves predictably, technicians on land can send test signals through the damaged line and analyze the reflections returning from the fault point. In a sense, the cable itself becomes an enormous sensor. By measuring how long it takes for the reflected signal to return, engineers estimate the distance to the break, sometimes within surprisingly small margins across thousands of miles of ocean. There is something eerie about that process. Humans sitting inside control rooms on land, listening to the silence of damaged light beneath the sea. But knowing where the problem probably exists is very different from fixing it. The actual repair operation may take days or even weeks before it fully begins. Specialized cable repair ships must first travel to the location, and those vessels are not stationed everywhere equally. Weather conditions matter. Ocean traffic matters. International permissions may matter depending on the region. During severe disruptions, entire governments and major corporations may monitor the repair timeline anxiously because modern economies depend so heavily on international connectivity. Yet once the repair ship finally reaches the area, the real difficulty is only beginning. Because unlike repairing infrastructure on land, the damaged cable is often lying thousands of feet below the surface in complete darkness. The ocean does not make retrieval easy. In shallow water, divers or remotely operated vehicles may assist directly. But in deeper regions, human beings cannot simply descend and grab the cable manually. Instead, crews rely on methods that sound strangely old-fashioned, considering the sophistication of the internet itself. Giant grappling hooks are lowered into the ocean and dragged slowly across the seabed in an attempt to catch the cable. The process resembles fishing more than futuristic engineering. Somewhere far below, the repair vessel, steel hooks scrape through darkness, searching for a line not much wider than a hose resting on an invisible landscape. And unlike movies, where advanced systems instantly locate everything, real operations can become frustratingly uncertain. Ocean currents shift equipment. Terrain complicates retrieval. Weather interferes. Sometimes the cable must be hooked and lifted carefully from depths exceeding several miles. The deeper the cable lies, the more dangerous and delicate the operation becomes, because the cable itself was never designed to support extreme lifting forces during retrieval. Tension must remain carefully controlled. Too much strain and additional damage may occur. Too little, and the cable slips away again into darkness. Some repair operations require repeated attempts before crews successfully recover the damaged section. When the cable finally emerges from the water, the image can feel surprisingly anticlimactic at first. A wet industrial line hauled slowly onto a ship deck beneath cold sea air. Yet that damaged section may represent a communication failure affecting millions of people across continents. It is strange how ordinary critical infrastructure often appears physically. The internet, once again, reveals itself not as a magical cloud, but as a vulnerable object made of real materials exposed to the same forces that damage ships, pipelines, and machinery. Once on board, the actual repair work begins. Technicians carefully cut away damaged portions and prepare the fiber for splicing. This stage requires extraordinary precision because fiber optic communication depends on light remaining nearly perfectly aligned across microscopic pathways. A tiny error in the connection can degrade the signal significantly. Engineers essentially perform surgery on light itself. Individual fibers are cleaned, aligned, fused together, protected, and tested repeatedly before the cable can be lowered back into the ocean. The level of patience involved is remarkable. Civilization often imagines internet infrastructure as automated and instantaneous, but submarine cable repair still depends heavily on highly skilled human labor, carried out under difficult conditions at sea. During major outages, entire regions may temporarily depend on the success of a few technicians working carefully aboard a ship drifting above invisible depths. Weather remains one of the greatest complications throughout the process. Heavy seas can halt repair work entirely because stable positioning becomes too dangerous. Waves constantly move the vessel. Wind alters tension dynamics. Equipment swings unpredictably. Even after the damaged cable is recovered, reconnecting and redeploying it safely requires calm enough conditions to avoid introducing new problems. In some cases, repair ships have waited offshore for days while storms passed overhead, unable to continue despite the pressure to restore connectivity quickly. The ocean dictates the schedule. That reality feels important because modern civilization often behaves as though digital systems somehow escaped dependence on nature. Submarine cable repairs expose the illusion completely. The internet still waits for weather. There are moments during repair operations when the entire system feels almost absurdly fragile. Billions of people relying on online services, while a handful of engineers somewhere in rough seas struggle to reconnect a cable beneath freezing black water. Yet, perhaps fragility is not quite the right word, because despite the difficulty of repairs, the global cable network has proven surprisingly resilient over time. Routes overlap, traffic reroutes, backup capacity exists. Complete collapse remains rare even during major failures. The internet was built with the expectation that damage would occur eventually. What surprises many experts is not that cables break sometimes, but that such an enormous planetary system functions as reliably as it does. Still, certain regions remain more vulnerable than others. Island nations often depend heavily on limited numbers of cables connecting them to larger global networks. In those situations, a single break can create major disruptions until repairs are completed. Some countries invested heavily in additional redundancy precisely because previous outages exposed how dependent modern infrastructure became on stable international communication. Financial systems, hospitals, emergency services, shipping logistics, and cloud computing all increasingly rely on constant connectivity. What once felt optional became foundational. There is also a psychological tension surrounding submarine cable repairs that extends beyond engineering. Every successful repair reminds governments and corporations how dependent they are on infrastructure most citizens never see. Some analysts argue this awareness is partly driving new investment in cable diversity and alternative routes. Others believe satellite systems may eventually reduce certain vulnerabilities, though satellites still face limitations in bandwidth and latency compared to fiber optics for many large-scale applications. Most likely, future communication systems will involve layered redundancy between cables, satellites, and terrestrial networks, rather than one replacing the other entirely. Civilization rarely abandons infrastructure that works. It usually builds additional systems around it instead. Some repair operations uncovered unexpected discoveries beneath the ocean along the way. Lost equipment, wreckage, geological features, even traces of older communication cables abandoned from previous generations of infrastructure. The seabed slowly accumulates layers of technological history, much like cities accumulate buried architecture over centuries. Victorian telegraph cables, Cold War systems, modern fiber optics, different eras of communication resting together beneath the sea. There is something haunting about that image. Human civilization repeatedly lowering its thoughts into darkness across generations, always trying to shrink distance a little further. And despite all the technology involved, many submarine cable repairs still retain a strangely physical quality that feels almost timeless. Ships moving across rough seas, hooks descending into darkness, crews working through cold nights under deck lights, machines pulling damaged lines from the ocean, one careful meter at a time. The internet may feel abstract from inside homes and offices, but out at sea, it becomes mechanical again, tangible, heavy, vulnerable to weather and gravity like every other human system. At night, during repair missions, the atmosphere aboard cable ships can become eerily quiet between bursts of activity. Beyond the deck lights, the ocean disappears into blackness. Somewhere beneath the vessel lies the broken line carrying fragments of civilization itself. Stock trades waiting to complete. Video calls rerouted across longer paths. Data centers compensating silently in the background. Most users never realize how much hidden adaptation occurs when submarine cables fail. The internet often masks damage remarkably well until disruption grows severe enough to surface publicly. In a sense, the network behaves almost biologically, rerouting around injury while repair crews work to restore damaged pathways. And perhaps that comparison is more accurate than it first appears. Because under the oceans, the cables really do resemble nerves connecting distant parts of a global organism. When one is cut, signals search for another route. The system survives, but not without strain. Yet even after the repair is complete and the cable disappears once again beneath the surface, another unsettling question remains quietly in the background. If these hidden lines beneath the ocean became so essential to civilization, who actually controls them in the first place? The deeper you look into the internet beneath the ocean, the stranger the question becomes. Because eventually, after the cables, the ships, the repair crews, the storms, and the hidden routes across the seabed, another realization begins to surface quietly underneath everything else. Someone owns these lines, or at least someone controls large parts of them. And once you start asking who truly owns the physical infrastructure carrying most of the world's communication, the internet suddenly stops feeling like a free-floating digital universe and starts looking more like a map of power hidden beneath the sea. At first, many people assume submarine cables must belong mainly to governments, perhaps because the system feels too large and important to exist any other way. But historically, much of the undersea network was built and operated by telecommunications companies. In the early days of submarine communication, telegraph corporations financed transoceanic cables because faster information meant economic advantage. That patterned into the modern internet era. Large telecom providers invested heavily in submarine infrastructure, connecting continents through landing stations and exchange hubs. But over time, something changed. The companies shaping the internet most aggressively were no longer just telecommunications firms. They were technology companies, cloud companies, data companies, companies whose entire business models depended on moving enormous amounts of information continuously across the planet. And eventually, some of the largest corporations in the world decided they no longer wanted to simply rent capacity on submarine cables. They wanted to build and control the cables themselves. That shift may end up being remembered as one of the most important infrastructure changes of the digital age. Because today, major technology companies, including Google, Meta, Microsoft, and Amazon, are deeply involved in submarine cable projects around the world. Some systems are owned jointly through partnerships. Others are partially controlled through consortium agreements. In certain cases, technology companies finance or manage major portions of entirely new transoceanic routes themselves. And the reason is surprisingly logical once you understand how modern computing works. The internet most people interact with is increasingly tied to giant cloud infrastructures distributed across continents. Streaming services, artificial intelligence models, social media platforms, search engines, remote data storage, massive server farms exchanging information constantly at enormous scale. Every second, unimaginable amounts of data move between facilities in North America, Europe, Asia, and beyond. Owning faster and more reliable communication pathways became strategically valuable. In some situations, even tiny improvements in speed matter. Fractions of a second can influence financial systems, cloud synchronization, gaming networks, or AI response times. Which means submarine cables are no longer just passive infrastructure. They became competitive assets. And that realization changes the emotional atmosphere around the internet. For years, digital culture encouraged the feeling that the online world existed everywhere equally, decentralized and detached from physical geography. But the physical infrastructure tells a different story. Information moves through very specific pathways. Certain landing stations became enormously important. Certain routes carried disproportionate amounts of global traffic. Certain companies gained extraordinary influence over the architecture beneath the ocean. The internet still functions as a distributed network overall, but it is not distributed evenly. Power concentrates around infrastructure. It always has. In earlier centuries, strategic ports shaped empires. Railroads shaped industrial economies. Oil pipelines shaped geopolitics. Today, data infrastructure increasingly shapes civilization itself. Some submarine cable routes became so critical that analysts refer to them almost like digital choke points. The Red Sea region, the Mediterranean, the Strait of Malacca. Narrow geographic corridors where huge volumes of international communication pass through relatively constrained spaces. The geography of the Earth still matters deeply, even in the age of cloud computing. And because these routes matter, governments pay attention to them, sometimes very closely. Public discussions about submarine cable security increased significantly in recent years, especially as geopolitical tensions between major powers intensified. Intelligence agencies, military planners, and infrastructure analysts increasingly describe submarine cables as strategic assets rather than merely commercial utilities. Some experts warn
that future conflicts could involve attempts to disrupt communication infrastructure beneath the sea. Others argue those fears are occasionally overstated, because damaging the global internet would create massive economic consequences for nearly everyone involved. The truth probably exists somewhere between those extremes. Modern economies became so interconnected that submarine cables now occupy a strange position between civilian infrastructure and national security systems. They carry ordinary social media traffic alongside banking systems, government communication, cloud infrastructure, and military coordination simultaneously. That overlap makes ownership questions far more complicated than they first appear. In some cases, cable projects involve partnerships between private corporations, telecom providers, and state-connected entities spread across multiple countries. One line crossing the ocean may involve legal agreements, landing rights, financing arrangements, and regulatory oversight from several governments at once. The infrastructure beneath the sea became global long before political systems fully adapted to managing it coherently. There are also growing debates about concentration of power. Some critics worry that as giant technology companies expand control over physical infrastructure, the internet itself may become increasingly shaped by a relatively small number of corporations. Others argue that these investments actually improve global connectivity because large companies possess the resources necessary to build faster and more advanced systems. Neither perspective is entirely unreasonable. Modern submarine cables cost enormous amounts of money to construct and maintain. Without major investment, global bandwidth growth would likely struggle to keep pace with rising demand. At the same time, dependence on a small number of dominant infrastructure players naturally raises concerns about influence, resilience, and long-term control. These tensions rarely produce simple answers, because the internet itself evolved faster than many political and legal frameworks surrounding it. There is another layer to this story that feels especially strange once you notice it. Most people interact daily with digital platforms owned by large technology companies without thinking much about the physical infrastructure underneath them. You open an app, stream a movie, upload photos, ask an AI system a question. The experience feels almost weightless. Yet, beneath that simplicity is an immense industrial network involving cables, landing stations, server farms, cooling systems, power grids, and transoceanic infrastructure stretching across the seabed. The digital world did not eliminate physical systems. It hid them behind interfaces smooth enough that most users stopped noticing they existed. And perhaps nowhere is that invisibility more complete than beneath the oceans. Some submarine cable landing stations are surprisingly ordinary from the outside. Small buildings near remote coastlines, fenced utility facilities, industrial structures with little indication that huge portions of international communication pass through them every day. Civilization's nervous system entering land through quiet coastal infrastructure most people drive past without a second glance. There is something psychologically fascinating about that contrast. Modern civilization increasingly depends on systems hidden in plain sight. Data centers disguised as warehouses, fiber routes buried beneath streets, submarine cables resting beneath dark water. The more important the infrastructure becomes, the less visible it often appears to ordinary life. This invisibility may partly explain why submarine cables still feel mysterious despite carrying the modern world. People naturally focus on what they can see directly. Satellites attract attention because they orbit visibly above Earth. Smartphones attract attention because they exist in human hands. But the physical pathways connecting continents remain largely hidden beneath geography and water. Yet the cables themselves quietly influence global economics, politics, communication, and culture every hour of every day. In some ways, they form a second invisible map of civilization layered beneath the planet, a hidden geography of information. There are also persistent questions about surveillance and monitoring beneath the sea. Over the decades, reports and declassified operations revealed that intelligence agencies sometimes viewed submarine communication systems as valuable targets for interception. During the Cold War, undersea cables occasionally became objects of covert interest precisely because so much important information flowed through them. Modern encryption dramatically changes many aspects of communication security today, and experts disagree on how vulnerable current systems may be under different circumstances. Some argue strong encryption makes large-scale interception far less useful than in earlier eras. Others believe physical infrastructure control still matters enormously, regardless of encryption, because access itself creates strategic possibilities. Much of that world remains intentionally opaque, making definitive conclusions difficult. But the existence of the debate reveals how important submarine cables became, far beyond ordinary internet traffic. They are no longer merely communication tools. They are part of the architecture of global power itself. And perhaps the most unsettling realization of all is how dependent modern civilization became on infrastructure most people rarely think about. Beneath oceans, beyond coastlines, hidden in darkness, enormous streams of human thought continue moving through cables owned, operated, financed, and monitored by overlapping networks of corporations and governments. The internet feels open because millions of people use it simultaneously, but its physical foundations remain highly organized, highly engineered, and deeply tied to economic and geopolitical systems in the real world. In another century, empires fought over sea routes carrying spices, gold, and oil. Today, some of the most valuable cargo crossing oceans is invisible, information itself, and the lines carrying it may become even more important in the future as artificial intelligence, cloud infrastructure, and global data consumption continue expanding beyond anything earlier generations could have imagined. The strange thing about the internet beneath the ocean is that it already feels futuristic. Yet many engineers believe humanity is still only in the early stages of what these systems may eventually become. Right now, somewhere in the darkness below the Atlantic and Pacific Oceans, pulses of light are carrying enormous portions of human civilization through cables resting silently on the sea floor. But the amount of data moving through those cables keeps growing at a pace that even experts sometimes struggle to fully predict. Streaming platforms became normal. Then cloud computing exploded. Then remote work reshaped communication patterns across entire countries. Now,
artificial intelligence systems are creating another wave of demand so large that some analysts compare it to the early rise of the internet itself. Every AI model trained across distributed data centers, every real-time translation system, every cloud gaming session, every ultra-high-definition video stream, every future technology requiring constant synchronization between continents pushes more pressure onto the hidden infrastructure beneath the sea. And because of that, the future of submarine cables is beginning to look increasingly strange. Modern submarine systems already carry astonishing amounts of information, but newer generations of cables are being designed for capacities that would have sounded absurd only decades ago. Advances in fiber optics, signal amplification, and wavelength multiplexing continue increasing how much data can move through a single cable. Engineers are constantly searching for ways to squeeze more information through strands of glass buried beneath the ocean floor. In some ways, the cables are becoming less like ordinary communication lines and more like planetary-scale data arteries feeding the metabolism of a digital civilization that no longer sleeps. The pace of global communication never truly slows now. Financial markets operate continuously across time zones. Data centers synchronize endlessly. Artificial intelligence systems process requests every second of the day. Humanity built a network that behaves less like a collection of machines and more like a living environment surrounding modern life itself. And as that environment expands, the ocean is quietly becoming even more important. One of the most fascinating developments involves turning submarine cables into something more than communication infrastructure. Researchers discovered that fiber optic systems may also function as enormous environmental sensors. Tiny vibrations traveling through the ocean can subtly alter the behavior of light moving inside the fiber. With specialized analysis, sections of submarine cable may potentially detect earthquakes, underwater landslides, ship movement, and even certain oceanographic changes. In other words, the internet cables beneath the sea might eventually help humanity observe the planet itself while simultaneously carrying digital communication. That idea feels almost surreal. Civilization accidentally building a giant nervous system beneath the ocean that not only transmits information but senses the environment around it. Some experimental systems already demonstrated promising results in detecting seismic activity through existing fiber networks. Researchers continue exploring how far this concept might go. Could future submarine cables help improve tsunami warning systems? Could they monitor underwater geological activity in real time? Could they contribute to climate science by tracking subtle ocean changes over enormous distances? The answers remain uncertain, but the possibility itself reveals how infrastructure originally built for communication may evolve into something much larger. And perhaps that transformation is inevitable. Once humanity covers the planet with connected systems, those systems begin generating new uses nobody originally planned for. Another idea gaining attention involves the Arctic. As climate change alters polar ice patterns, some planners and governments started examining the possibility of future submarine cable routes crossing through Arctic regions. On paper, certain northern routes could potentially shorten communication distances between major continents. Shorter routes may reduce latency, which matters for financial systems and cloud infrastructure. But the Arctic introduces enormous engineering and geopolitical challenges. extreme conditions, remote logistics, environmental concerns, and strategic tensions between nations all complicate the picture. Some experts believe Arctic cable routes could become increasingly important over coming decades. Others argue the difficulties and risks may limit how practical those systems truly become. Either way, the discussion itself reveals how aggressively civilization continues searching for faster and more efficient ways to move information around the planet. Even the most remote environments on Earth are now being considered through the lens of digital infrastructure. There is also growing interest in autonomous maintenance systems. Today, repairing submarine cables still requires specialized ships, human crews, and physically recovering damaged sections from the sea floor. But future systems may become more automated. Some researchers envision robotic underwater vehicles capable of inspecting or even repairing portions of infrastructure independently. Fully autonomous deep-sea repair networks remain technically difficult, especially given the extreme pressures and unpredictable conditions involved. But the direction of the research reflects a broader trend. The internet increasingly depends on infrastructure too large and complex for constant direct human oversight. Automation becomes attractive almost automatically once systems reach planetary scale. Yet the ocean remains stubbornly resistant to easy solutions. Machines fail underwater in ways difficult to predict. Communication delays complicate remote operations. Saltwater corrosion affects everything eventually. And unlike software, physical infrastructure cannot simply be patched instantly from afar. The ocean forces technology to remain material. That tension between digital ambition and physical reality may define the future of submarine infrastructure more than any single invention. Some of the strangest experiments are happening not just around cables, but around the data centers connected to them. In recent years, companies explored underwater data center concepts, where sealed computing systems operate beneath the ocean itself. One major experiment suggested that underwater cooling environments could potentially improve energy efficiency and hardware stability under certain conditions. The image itself feels almost science fiction. Pieces of the internet literally operating underwater while connected through submarine cables nearby. Some experts believe future computing infrastructure may become increasingly distributed geographically as energy demands rise and artificial intelligence systems require larger computational resources. Others remain skeptical about how practical large-scale underwater deployment truly is over long periods. But once again, the broader pattern remains clear. The internet is moving physically outward into environments earlier generations never imagined as part of digital civilization. Space, polar regions, deep ocean infrastructure, remote autonomous systems. The boundaries between natural environments and technological systems continue blurring. At the same time, satellites are transforming global communication in ways that raise new questions about the future role of submarine cables. Low Earth orbit satellite networks changed what many people imagine internet access can look like. Remote regions once difficult to connect may now gain faster internet through constellations orbiting above Earth. The technology is genuinely significant. But despite the excitement surrounding satellites, most experts still believe submarine cables will remain the backbone of global internet traffic for the foreseeable future. The reason is partly physics and partly scale.
Fiber optic cables can carry enormous amounts of data with extremely low latency and relatively stable performance compared to satellite systems handling massive international traffic volumes. Satellites excel in coverage and flexibility, especially for isolated areas or mobile communication. Cables excel in raw capacity between major population and infrastructure centers,
which means the future may not involve one technology replacing the other, but increasingly layered systems working together. Space and ocean becoming interconnected parts of the same global network. There is something fascinating about that possibility, because it reveals how civilization solves problems repeatedly through redundancy. Humans rarely trust one pathway completely once dependence becomes critical enough. We build backups, alternative routes, overlapping systems, multiple ways for information to survive disaster or disruption. In some ways, the modern internet resembles a biological organism developing additional circulatory systems as it grows larger and more dependent on constant flow. And all of this expansion is happening mostly out of public sight. Most people never think about submarine cables while watching videos or asking AI systems questions late at night. Yet every increase in digital dependence pushes further demand onto these hidden networks beneath the sea. Artificial intelligence may intensify that pressure dramatically. Training large AI models already requires immense computational coordination between data centers spread across regions and continents. Future systems could demand even greater levels of global synchronization. Some analysts believe AI infrastructure growth may become one of the major drivers behind the next generation of submarine cable investment. In that sense, the future of artificial intelligence may depend partly on the future of undersea fiber networks lying silently in darkness below the ocean surface. There is also a philosophical side to all of this that feels difficult to ignore once the pattern becomes visible. Humanity keeps building systems that reduce distance between people, machines, and information. Telegraph cables shrank oceans psychologically in the 19th century. The internet accelerated that collapse of distance further. Now, artificial intelligence and cloud systems may push civilization toward even more constant planetary synchronization. The Earth itself increasingly behaves like a connected computational environment. Yet the infrastructure enabling this transformation remains deeply physical. Glass fibers, steel armor, ocean routes, cooling systems, power grids, repair ships. The digital world never escaped matter. It simply buried itself deeper inside it. And perhaps the strangest possibility of all is that future generations may eventually see today's submarine cable systems the way modern people now view early telegraph lines: revolutionary, but primitive. Quantum communication research, advanced photonic systems, AI-managed routing, autonomous infrastructure, and technologies not yet invented could reshape global communication again over the coming decades. Some predictions will fail. Others may transform civilization in ways difficult to foresee clearly from the present moment. But one pattern already seems likely to continue. The oceans will remain part of the story. Because despite all the futuristic visions surrounding the internet, humanity still keeps returning to the same ancient geography. The same seas crossed by trade ships, empires, migrations, wars, and exploration for thousands of years. Only now, instead of carrying spices or gold, the oceans increasingly carry thought itself. And perhaps the most remarkable part is that billions of people participate in this system every day without ever imagining where their information truly travels once it disappears into the screen. Tonight, somewhere beneath the Atlantic Ocean, pulses of light are moving silently through glass fibers in complete darkness. A teenager in California sends a message that crosses underwater mountains before reaching Europe in fractions of a second. A hospital transfers medical records between continents, while most of the patients inside the building sleep unaware. Financial markets exchange data constantly beneath storms and moonlight. Artificial intelligence systems synchronize between distant server farms. Entire governments communicate through cables resting quietly on the seafloor. And above all of it, the ocean looks empty. That may be the strangest part of the modern world. Civilization increasingly depends on systems almost nobody can see. The internet often feels invisible because its physical body was hidden beneath water, underground tunnels, server facilities, and remote coastlines until most people stopped imagining it as a real machine at all. But once you understand submarine cables, the illusion becomes impossible to fully recover from. The internet stops feeling like a cloud and starts feeling like infrastructure. Heavy, vulnerable, physical. Suddenly, every search result, live stream, online payment, GPS update, cloud backup, and AI request begins carrying a strange new weight, because you realize the modern world is not floating above the earth. It is tied directly into it, buried inside it, resting beneath the ocean floor. There is something deeply human about that realization, because it reveals that every technological age still depends on material systems underneath the abstraction. Ancient civilizations relied on roads and rivers. Industrial societies depended on railroads and electrical grids. The digital age depends on fiber optic cables stretched across the seabed, carrying pulses of light through darkness. The tools changed, but the pattern remained surprisingly familiar. Human civilization always builds invisible structures beneath daily life until people forget those structures exist. Most of the time, the internet feels immediate and effortless because users interact only with screens. Touch a button and information appears. Send a message and it arrives almost instantly. Ask a question and remote servers respond within seconds. The complexity underneath disappears behind smooth interfaces designed specifically to hide friction. But the friction never truly vanished. It merely moved elsewhere, out into the oceans, into cable landing stations, into massive data centers consuming enormous amounts of electricity, into repair ships waiting near strategic routes, into quiet buildings along coastlines where the modern world enters land from beneath the sea. In some ways, digital civilization became possible not because humanity eliminated physical limitations, but because it became exceptionally good at hiding them. There is also a strange emotional contradiction at the center of all this. The internet helped shrink the psychological distance between continents more than almost any previous invention in human history. People separated by oceans can now speak instantly. Entire global communities formed around shared interests, regardless of geography.
Information crosses the planet continuously at speeds earlier civilizations would have considered supernatural. Yet making that world possible required building one of the largest physical infrastructure systems humanity has ever attempted. The more virtual modern life became, the more physical infrastructure it quietly demanded underneath. That contradiction feels important because it says something deeper about technology itself. Humans often imagine advanced systems becoming less material over time, but the opposite frequently happens. Greater complexity usually requires larger, hidden foundations. Artificial intelligence depends on data centers. Streaming depends on transoceanic bandwidth. Cloud computing depends on electricity grids and cooling systems. Even wireless communication ultimately relies heavily on physical networks beneath the surface. The digital world did not escape the laws of geography or engineering. It merely buried them where fewer people would notice. And beneath the oceans, those buried systems continue expanding. New submarine cables are laid constantly because the appetite for data keeps growing. Every year, more human activity moves into digital systems. Education, banking, medicine, entertainment, navigation, commerce, government operations, scientific research, remote work, artificial intelligence. Civilization increasingly behaves as though uninterrupted connectivity is not optional, but fundamental. There are moments when it almost feels as if the planet itself is developing a second, invisible nervous system layered beneath the natural one. Signals moving endlessly between continents while billions of humans sleep, work, argue, learn, trade, and communicate above the surface. In another century, people measured national power partly through fleets and railroads. Today, enormous influence flows through data infrastructure hidden beneath the sea. Yet despite how advanced these systems became, they still remain strangely fragile in certain ways. Storms can interfere with repairs, anchors can sever cables, earthquakes can reshape seabeds, power failures can disrupt landing stations, political tensions can complicate infrastructure planning. Even the future of the internet itself increasingly depends on decisions involving energy consumption, climate stability, semiconductor manufacturing, and global supply chains. The deeper you look, the less the digital world feels detached from reality. It feels completely entangled with it. Some experts believe future generations may eventually view submarine cables the way modern people view early railroads or telegraph lines. Foundational systems that quietly reshaped civilization more than most individuals realized while living through them. That possibility seems increasingly believable. Because submarine cables did not merely accelerate communication, they changed humanity's relationship with distance itself. Before global networks, oceans slowed civilization down. Today, oceans carry civilization through themselves continuously. And perhaps that transformation subtly altered human psychology as much as technology. Entire generations grew up assuming information should move instantly. Waiting weeks for news from another continent now feels almost unimaginable. The planet became psychologically smaller because hidden infrastructure beneath the ocean made it feel that way. There is also something strangely beautiful about the image itself once you stop thinking of the internet as purely digital.
Somewhere far below the waves, in water colder than ice cubes floating in a glass, cables lie silently across ancient geological landscapes. Volcanic ridges, abyssal plains, deep trenches shaped over millions of years before human civilization existed. And through those cables moves modern human thought at extraordinary speed. Songs, memories, arguments, medical discoveries, scientific research, political debates, family photos, artificial intelligence conversations, entire fragments of civilization flowing through glass fibers resting in darkness older than humanity itself. The contrast almost feels poetic. Ancient Earth carrying modern consciousness beneath the sea. At night, the illusion becomes even stranger. Cities glow above the surface, while data races invisibly below them. Airplanes cross the sky, carrying sleeping passengers who never think about the oceans underneath. Millions of people scroll through videos in bed, while storms move across the Atlantic, far above the cables delivering those videos. Somewhere offshore, maintenance ships wait quietly near strategic routes. Somewhere else, engineers monitor traffic flowing between continents in real time. The machinery of global civilization continues operating even when almost nobody notices it happening. And perhaps that hidden continuity is part of what makes modern life feel stable. Most infrastructure works best psychologically when people forget it exists. We rarely think about water systems until pipes fail. Rarely think about power grids until lights go out. Rarely think about submarine cables until the internet slows unexpectedly and news headlines suddenly mention damage beneath the ocean. The hidden systems become visible mainly during moments of disruption. Yet they shape ordinary life constantly. There is another possibility worth considering as humanity moves deeper into the digital age. The future may not make submarine infrastructure less important. It may make it even more essential. Artificial intelligence systems already demand extraordinary levels of global data transfer. Future computing environments may require even larger communication networks between continents. Autonomous systems, cloud robotics, real-time translation, immersive digital environments, and technologies not yet invented could push global bandwidth demand far beyond current levels. If that happens, the oceans beneath the planet may become even more densely woven with communication infrastructure than they already are. Civilization could continue building an increasingly complex hidden layer beneath the sea, while ordinary users remain largely unaware of its existence. And maybe that is the final strange truth hidden inside all of this. Humanity spent centuries fearing the ocean as a barrier. Storms swallowed ships. Distance isolated civilizations. Messages disappeared into water for months at a time. Yet, eventually, humans turned the oceans into pathways for thought itself. Not by conquering them completely, because the sea still resists control in countless ways, but by learning how to lay fragile lines through darkness and trust they would hold long enough to connect the world together. The internet beneath the ocean is not really a story about cables alone. It is a story about civilization trying to overcome distance again and again, using whatever tools it can invent. And tonight, While most of the world sleeps without thinking about it, those invisible rivers of light are still moving silently beneath the waves, carrying pieces of human life across the planet through the cold darkness at the bottom of the sea. Thanks for exploring the hidden world beneath the ocean with me tonight. If you still have questions about how the internet really works, leave them in the comments and I'll do my best to explain. Sleep well, and thanks for watching Sleepy Systems.